Welcome back to Algorithms and Uncertainty. I'm super excited that we're starting a new topic, a new direction today. So far, when we were talking about online algorithms, we assumed to have no prior knowledge whatsoever. So indeed, our algorithm had to be prepared for anything that could happen. Now we change this assumption and we assume to have some prior knowledge. How do we do this? Well, we assume that somehow the input is coming from some sort of probability distributions. This is what we want to formalize later on in the general framework of Markov decision processes. But before we getting there, let me introduce a motivating example which we will be able to solve by the end of today's lecture. Suppose you're participating in a game show and you can win lots and lots of money by simply opening envelopes. And this is what these envelopes look like. Each of them have an amount of money which you might find inside and a probability that this amount of money is actually in the envelope printed on them. Now you may just open envelopes, you may keep opening envelopes up to the point where you open an empty envelope. Then your game ends. In which order would you want to open the envelopes? For example, with these two, would you rather start with this envelope, this white envelope, where you find actually only a small amount of money but with a decent probability? Or would you take the chance and take this brown envelope where you will find a much higher amount of money but with a smaller probability? Now in this case, if you do the math, you'll figure out that in both cases, the expected amount of money that you'll find inside is actually 100 euros. So it seems reasonable to first start with this envelope where you have a higher chance that it is actually non-empty, because this increases the chance that you can actually open a second envelope. Whereas if you start with a brown envelope and only then open the white envelope, then chances are that you're not getting anything, and the chance is much higher that you're not coming to the second envelope at all. Good, but now there are many other envelopes. For example, this one here. This only has 3 euros inside, but with a pretty high probability it's non-empty. Would you want to open this first? Because it means that, well, most likely you will go home with at least 3 euros. Or is this 1% chance that it is actually empty? Is this too high? Because then this means you cannot open the envelopes with the really high prizes. Well, this exactly we will be figuring out today. By the end of today's lecture, you will actually know how to solve this problem, which envelopes to open in which order. But before we're getting there, we should introduce the general framework of Markov decision processes. We will now introduce Markov decision processes, which allow us to not only capture this game with the envelopes, but many stochastic optimization problems. And also they play a huge role in machine learning, in particular in reinforcement learning. You may actually have already seen Markov decision processes, but even if you haven't, we'll now start by the very basic definitions. So what do we have? In a Markov decision process, we have a set of states and a set of actions, and then we choose in every round, we are in a state, we choose one action, and this leads us to a new state and gives us a certain reward. And our goal is to maximize the overall reward that we're getting. So let's formalize this. So we have a set of states, which we will call S, and a set of actions, which we will call A. And now we have a reward for taking action A, so small a, in state small s. This we will write as RW R subscript A of S. And now, when we're taking an action, we move to a different state. And this is defined by transition probabilities. So when we're taking action A in state S, we move to S prime with probability P subscript A of S, S prime. And this is, of course, a real number in 0, 1. This reward, by the way, is just some arbitrary real number. The reward may also be negative, which corresponds to us just paying a cost. And what will the process now be like? We will start from some state S1, and then we will choose one action, and then we get to another state. And so overall we will be getting a sequence of states which will be S1, S2, and so on. And importantly, these are random variables, so these states, those are random, and we get there, the probabilities that we get there are exactly defined by these PA, so the ST plus 1 is distributed according to PA ST, and then the second coordinate is just any possible state which we might be reaching for any fixed A and ST. Good. What does this mean? This now means that actually for the state that we are reaching, or for these probabilities, only the current state matters and the action that we're taking, not the history, that how we got there. And this is why this is called Markovian, because here only the ST matters, not S1 through ST minus 1. Good. Have you seen these things before? Probably, I think you've at least seen special cases of this. Namely, well, one thing that you've probably seen before is a deterministic finite automaton. In which these probabilities are just either 0 or 1. So these PA of SS prime are in 0, 1, which means there is exactly one S prime that we will be reaching for every A and S. So in a deterministic finite automaton, what you do is, well, you usually understand this as reading symbols from some alphabet from a word. Now you can equivalently interpret this as actions being taken. And these symbols from the alphabet, or alternatively these actions, they take you through states. And this happens deterministically. And what you then have is that the next state is always determined deterministically based on where you currently are. Importantly, it does not matter how you got there. The only thing that matters is where are you now and what's the action being taken. Another special case is a Markov chain. There we'll have that the number of actions is only 1, which means that there is only one action, like maybe something like continue, and then you're just moving randomly through these states, and what you're then interested in is what sequence of states is evolving. So they're actually the kind of a problem that we want to solve, namely, which actions should I choose to get a higher reward? Those are actually not interesting because you can only choose one action. By the way, in a deterministic finite automaton, you're usually not interested in a reward either. You're just interested in whether your word that you're reading gets accepted or not, which might also you might also model in terms of a reward, but this is usually not what you're very interested in. Here, in this case of a Markov chain, you actually do have this notion of a reward, that you're getting something out of this, and you wonder, how much am I getting? For example, if you're considering a random walk or something like this. But there you're not taking any actions. But those are just two special cases of what you can actually capture by Markov decision processes. But what is even more interesting is, of course, our example with the envelopes that we had at the very beginning. So how would we capture this? So once again, we have, now generally speaking, n envelopes, and envelope I contains the prize Vi, with probability Qi and is empty otherwise. And we may keep opening envelopes and keep all prices as long as no empty envelope is opened. What will we have to define now? We will have to define states and actions that we can choose. As the set of states, I will take the following. There are different ways of modeling this. I will define this now as follows. In the state space, I want to keep track of which envelopes have already been opened. And I do this by taking as possible states the power set of the set of envelopes. So there I'm keeping track of which subsets of the envelopes have already been opened, so that I don't allow an envelope to be opened twice. And then I have one further state, which is stop. Why do I have this stop state? Because I want to keep track of whether one of these envelopes has already been empty. What are the actions? The actions are nothing but opening envelopes. So we'll have one state for every one action for every envelope. And now what we'll have to define is the transition probabilities and of course also the rewards. What are the transition probabilities? Well, we'll have, for a state in which no envelope has been empty so far, we will now set the transition probabilities as follows. We will either move just to the state where envelope A has also been opened. So action A means just opening envelope A. And now we are just moving from the set of envelopes S having been opened so far to that envelope A has been opened as well. But it may also be that this envelope is empty, in which case we will be moving to the stop state. And then we'll of course have to also specify that all these other transition probabilities are simply 0. So we cannot reach any other state. And then we'll also have to specify what happens if we take any action in the stop state, then we remain in the stop state. Good. Now this captures exactly what is supposed to happen, namely in the state space we're keeping track of which envelopes have already been opened and has one of these envelopes been empty. Now what is still allowed by this is that actually an envelope is opened twice. And why aren't we forbidding this? Because here we just cannot forbid this. Why can't we forbid this? Because we are now stating this that in every state, every action can be chosen. This is just because it simplifies our life later on. Now, how do we still forbid, or how can we forbid that an envelope is opened twice? Well, what we do is we just give it a super punishing reward. That you would never want to do this, that you would want to do everything else before opening an envelope a second time. And this is exactly covered by our rewards. We will set that RA of S will be QA times VA if A is not in S. So if this envelope A has not yet been opened, then, okay, actually this is now random, but we are just taking the expectation here. So we are taking the probability that this envelope is non-empty times the price that we find. Once again, this is happening if we are in a state which is not the stop state, of course. So S should be again such a set of envelopes that have been opened so far. And what else do we say? Okay, we say that the reward is negative infinity if the envelope has been opened before. And also, if we're in the stop state, then we'll have to define and also if we're in the stop state, then we'll have to say what happens when we're choosing an action, because also there we're not forbidding somebody to still take actions, but what we're saying is, okay, this doesn't give any further reward. So this is expressed by this definition. So these rewards are generally a little complicated because, of course, as I was saying, in every state, every action might be chosen. You could also picture the setting in which we would only allow a subset of the actions to be chosen in every state. This might make things simpler here, but taking the more general perspective, this might make things actually more complicated. Because then we would have to define a set of possible actions for every state. Now we are just capturing this by the fact that we have this very punishing reward when we're not supposed to take one action in a certain state. And now this entire process runs for n steps. And afterwards, we have opened maybe even all envelopes. Maybe we've reached the stop state before. Then, of course, we're still opening. We still have to choose actions, which means we're still kind of opening envelopes, but this isn't giving us any reward. This isn't moving us anywhere, so effectively the game is already over once we reach the stop state for the first time. But this just keeps our modeling here simple that, well, it is still allowed to just open envelopes. Now what we want to do is we want to figure out what is the best thing that you can do here in such a Markov decision process. And this thing is called a policy. And next we will first define what is a policy, and then we'll also see how do we compute the best policy. Now we've seen already the definition of states and actions, of transition probabilities and rewards, but what we don't have so far is the notion of what is actually happening. How are these things evolving? How are we getting anywhere? What is it that we're actually doing? And what we're doing is actually we are devising a policy. What is a policy? A policy just tells us for every state in the Markov decision process, or more generally speaking, for any history of however we got to a state in a Markov decision process, it tells us what we want to do next. Let's try to formalize this. So a policy defines to each sequence of states S1 through St-1 an action pi of S1 through St-1. This is of course coming from the actions. So this means that if we now if we're now starting from state S1, we will choose action A1 superscript pi. So this is the action that the policy tells us to choose, and this is pi of S1. Then this will take us to some state S2, which I'll now also use as superscript pi because this is where the policy is taking us. And then we will now choose A2 pi, which is pi applied on S1, S1 to superscript pi, and we will now reach a third state, and then we will choose a third action, which takes us to a fourth state, and so on. And what's the objective? What do we care about now? We care about the expected reward of policy pi in capital T steps. So this will be V of pi S1 comma T, And so this is the expectation of the rewards that we are collecting up on the way, because we're always taking these actions RT superscript pi, and we're choosing them in the states ST superscript pi. So this is the expected reward that the policy will be collecting. Now, in contrast to an online algorithm, we can now just define what kind of policy maximizes this quantity. And this is what we call an optimal policy. Maybe I should have mentioned that we actually assume now for simplicity that these the set of actions is finite, although this doesn't make a huge difference, but otherwise it might be that you have some strange effect that the maximum doesn't exist, only the supremum exists, but this will actually never happen for us. So don't be annoyed by this. We will now just say the question, we call pi an optimal policy if this term here is maximized. And moreover, we can define v star of s1, t as the maximum of which any policy pi will give us when we started from state S1 for capital T steps. So what we are interested in now is which policy pi gives us actually the highest possible reward, which policy pi maximizes this v pi of s1 v of pi comma s1 comma t. How do we find this policy, and maybe also how big is this quantity? Can we calculate this? This thing here, of course, we can assume to be able to calculate, because we are now assuming to have finitely many actions, finitely many states. So this is just something that you can actually compute. But how would we compute this? Because we have this weird maximum floating around. And is this difficult or not? Well, fortunately, it is not difficult because of the structure of the optimal policy. So what is it that is happening here? If we let pi be an optimal policy, then how big is v star of s1 comma t? Well, this is nothing but exactly v of pi comma s1 comma t, because this is how we define or what we require from an optimal policy, that this is actually, that this term here is maximized. Now, how was this here defined? It's exactly defined like this. So we might as well write the expected reward that we are collecting through the course of the t time steps. Now, let's take out the very first step, because this isn't even random. The first action and the first state are no random variables. So the question is, how big is this here now? This, of course, depends on many random variables, for example, the states that we're in. Even the very first state, which is S2 pi, is random because it depends on where the probability distribution, when we're taking this R1 pi in the first step from the state S1, where this is taking us. But this is something we can write out explicitly. We can now take the sum over all states S prime and now ask what's the probability that in our first step we're getting from S1 to S prime, and then we are interested in a conditional expectation here where we condition on the second state being S prime. And now the amazing thing happens, namely, how big is this here? How big is, let me write this down once again, the expected reward that we're getting from our optimal policy from steps 2 to t if we start in state S prime. And this is nothing but the expected reward if the start state was S prime and we were running for only t minus 1 steps. Why is this true? Because we would have to say, well, this is both smaller and larger, or no smaller and no larger, what we have on the left-hand side and on the right-hand side. Good. Well, how does one make such an argument? I won't go into super formal details here because this gets a bit annoying. But what is happening here is that for this part, what does this mean? This now means that what is the expected reward that you're getting from steps 2 to t from the optimal policy conditional on that the second state that you're in is S prime. Here we are asking what is the expected reward if you're starting from S prime and you have only t minus 1 steps. And let me maybe argue about this part because we have more of notation for this now. The other part is just the same. And to this end, you can now suppose that we have a strict inequality, that the left-hand side is strictly smaller than the right-hand side. Then we can improve pi by following an optimal policy from the second state on, and by this I mean ignoring, we have to ignore that the first state S1 was even ever visited. So here we are using the fact that this Markov decision process is Markovian, which means the rewards and transition probabilities, they only depend on the current state and the action that is being chosen. They do not depend on how we got here. And because this is true, it doesn't actually matter whether here there was actually a state S1, here and there was no state S1, we are just starting from S prime right away. But effectively, in both cases you can do exactly the same because the Markov decision process really doesn't care whether we were in an earlier state or not. The Markov decision process forgets everything that is not explicitly stored in the states. Good. So this kind of an argument you can actually make more formal if you like, but in the interest of time and because I feel that this is not super interesting, I'm not doing this here in class, but I'm rather just coming to the conclusion namely that this V star of S comma T, which was what? Recall what it was? It was, what's the expected reward of an optimal policy starting from S1 or from S for T state for T steps. This is the maximum. Take the maximum over all possible actions. This is the first action that you're choosing. And then, because this is what is actually now coming out of this here, we ask what is the reward that we're getting for the first step, plus then where are we getting from there? So we are now taking a random transition from S to some S prime, and then what we're getting from there is the reward V star of S prime, comma, T minus 1. So what's now the point? The point is actually that this equation holds. The expected reward that we're getting from an optimal policy, if we're starting from a state S and we have T steps, is exactly given by this recursive formula. So here what you'll see is, okay, we again have the reward of an optimal policy starting from some state S prime, but only going for T minus 1 steps. And then we have here the reward of our first action and the random transition probabilities where we are getting with our first transition. And I hope you now have already an idea how this can help us to compute an optimal policy. Namely, we will just have to figure out, or the thing that we'll have to do is we'll only have to compute V star of S comma T, and then we'll have to see, okay, which actions are it that actually attain this maximum here. And this means nothing but that we can compute an optimal policy actually via dynamic programming. And what we will be showing is the following. An optimal policy for a time horizon of capital T steps can be computed in time O of T times the cardinality of the state space squared times the cardinality of the action space. Moreover, the computed policy is Markovian. Before I say something about this last sentence, let's first talk about this first sentence. This means now we can actually compute an optimal policy, and the running time looks okay at first sight. We'll come to this, whether this is really okay or not, in a second. But what will be the running time? It will be the time horizon times the number of states squared times the number of actions. But there's something special about this policy, namely that it is Markovian. So far, I've only talked about the decision process being Markovian, meaning that all that matters is the state we're currently in and the action that we're taking. And this is exactly, or the fact of a policy, the property of a policy being Markovian is exactly the same. Only the only things that matter for our decision are the current state and how much time is left. So let's write this down formally. A policy pi is Markovian if the actions only depend on the current state and the number of remaining steps. We then write pi of s comma t prime for the action being taken in state S when t prime steps are remaining. Good. So this is just trying to formally write down what I was just mentioning, that we now have for every state and number of remaining steps, we just define one action and not for every possible history, because, and this is actually quite intuitive, what the states that we saw earlier don't actually matter. All that matters is the state that we're currently in. And now we can actually define, we can actually prove the theorem. How do we prove this? What was the theorem asking us? Well, an optimal policy can be computed in this much time. Well, what we will do is we will use dynamic programming. We will initialize v star of s, comma 0 being 0. This would be the reward that we would get if there were no steps at all. That's of course 0. And now for capital T prime from 1 to capital T, what we will do is the following. For all states, we will now set v star of s comma t prime. So this is the expected reward of an optimal policy starting from state s with t prime steps remaining. This is nothing but the following. Take over all actions, maximize the reward that you're getting now, plus take a random transition to a new state, and now ask yourself, what is the expected reward that you're getting from this point onward, with only t minus 1 steps remaining. And this is already enough in terms of dynamic programming to compute us all these v star of s comma t. We can of course extend this by saying that pi of s comma t prime is now any action that maximizes this quantity that we wanted to maximize. Now, by this construction, we will have that v of pi comma s comma t prime will be equal to v star of s comma t prime for all s and t prime, which means that pi is an optimal policy. And it is Markovian just because this way we define it right here is actually Markovian. We make our decision only depend on the current state and the remaining time, not how we reach this state. And what about the running time? The running time is, well, how many of these iterations do we have? We'll have capital T, many iterations on the outside, then we'll have capital S, or cardinality of S, many iterations for the inner for loop. And then how long does this take here? Well, that's maybe not super obvious. We will now take, for every action, we'll have to now take a sum over cardinality of S, many terms in here. So just executing this line here takes cardinality of A times cardinality of S many steps. So these are, I should maybe write an O here, because these were the number of iterations. and this was just one iteration. So what we're getting with this is O of t times cardinality of S squared times the cardinality of A. And this proves our theorem. Good. So there's nothing super mysterious about this proof. What I actually don't really like is that there is so much you'll have to define first before you can actually get to this point. And if you're still with me, I can tell you, well, now things are actually become nice. Why is this? Because now we just have one formula which we will be using for the optimal policy. We even have an algorithm that can compute us the optimal policy. Maybe let's see how this algorithm will work in the example of our envelopes. Coming back to our example with the envelopes, let's now say that, okay, once again recall that I already said that we'll have capital T rounds because all envelopes can be opened. In principle, of course, maybe we'll stop early. And now, what does happen more concretely? Well, for example, we might have V1 as 1000, Q1 as 1 over 100, and V2 equal to Q2 equal to 1. So this is more or less the same example that I had earlier. The numbers are a little easier. I have one envelope which contains 1000 with a probability of 1%, and I have another envelope which contains 1 with probability 1. So what does our intuition tell us regarding in which order to open the envelopes? Well, definitely we'll first want to open this envelope because we will find something in there for sure. And then we want to open that other envelope because there, well, we will maybe find something, then we're super happy, but maybe not. Then the game is over, but we don't actually care because this was the last envelope to be opened. So what's the expected reward that we're getting from this policy? It is 1 from this envelope, and then it is 10 from this envelope. And let's see how we're getting this with our algorithm that uses dynamic programming. So what we're interested in is the following. We'll have T prime as 0, 1, and 2. So this is how many time steps are remaining. And now we'll have to, for every state, what are our states? Our states are which envelopes have been opened so far. And the states that have been opened, so the possible envelopes that have been opened so far are all subsets of the set 1 and 2. Good. And we also have, of course, the stop state. Now, how do we fill this table? Well, the first thing that we do is we fill out this first row. If there are no time steps, then nothing is happening. We are not getting any reward. And now we are filling out this row. How do we do this? Maybe let's go back to our algorithm. In our algorithm, what do? We ask which of the actions maximizes now the current reward that we're getting plus the expected reward if we are going from here to a different state, and then from this point onward we're getting the optimal reward, but of course with only t prime minus 1 steps. So here this should be t prime because we are iterating over t prime from 1 to t. Good, so this means now, how do we fill out this row here? Let's fill it out from left to right. What do we fill in here? Well, this means there's only one time step left. No envelopes have been opened so far. And what do we now do? We can either open envelope 1 or open envelope 2. Then we are moving to these respective states. So we will either be moving to, let me draw this now in blue, we are either between this and this, or now in red we can be moving to this state for sure. In this case we really see it doesn't make any difference at all which state we're moving next to. So what you can then realize here is that, okay, here you would actually open envelope 1. And envelope 1 would give you an expected reward of 10. So let's maybe even draw this here in blue. Now the next entry is maybe a little more interesting. Here we have already opened envelope 1. Now we can decide, well, what can we decide? Either we can open again envelope 1, which will give us a reward of negative infinity, or we can open envelope 2, which gives us just a reward of 1. Which means now we will say, okay, here we are taking this 1, we will only open envelope 2. Now here, envelope 2 has already been opened. We can now decide, well, to open again envelope 1 or 2. 2 makes no sense now, so we'll open envelope 1, which will give us an expected reward of 10. Here, both envelopes have already been opened. We have to open one envelope now. Regardless of what we do, we're getting negative infinity. And here, regardless of what we do, we're getting a reward of 0. Now let's talk about this entry here. There are 2 steps. We can decide to first open envelope 1, or we can decide to open envelope 2. If we decide to open envelope 1, then we once again use the same colors that we were using here. If we are opening envelope 1, then we will move to either the state where we open envelope 1, or either this can be empty. The alternative is that we open envelope 2. And what do we want to do? What are the alternatives? If we open envelope 1, then with a probability of So we will definitely get a reward of 10, but then with a probability of 1 over 100, we are getting 1, and with a probability of 99 over 100, we are getting a reward of 0. Alternatively, if we are opening envelope 2, we will get an immediate reward of 1, and with probability 1, we are getting another reward of 10. And what is the bigger of the two? This here is 10.01. This other thing is 11. Which means here we will actually do this 11, which by the way is exactly what I was claiming earlier, that here we would want to open envelope 2 first. So we would want to do the red thing here and only then take the chance of opening envelope 1. Now let's fill out also the rest of the table. You will get negative infinity and 0 for the other entries, because here you would have 2 steps, but one of, or even 2 of the envelopes have already been opened, so you cannot actually avoid to open an envelope twice. But the important thing is actually only these states are the ones that are reachable from the initial state. So only from this point onward, we're actually not able to reach what's up here or what's down here. All this we cannot actually read. Only the marked states we can reach at all. But our algorithm didn't even care too much. The algorithm just fills out the entire table, although some of the states you might actually not ever reach. So maybe it's in some cases it will be more efficient to actually only compute the entries that you're actually interested in, but that would make just my statement of the algorithm a little more complicated, and I wanted to keep things very simple here. Good, so now we would be able to write an algorithm, to write a simple program that computes which envelopes to open in which order. But what would be the running time of this? This would be huge, because we have really many states. We have 2 to the n states, 2 to the n plus 1 states here. So the running time would be something like, what was our running time? T, which in this case is n, times number of states squared, which would be like 2 to the 2 times n, so 4 to the n. Number of actions would only be n, but it would still be awfully high, because this is because the number of states is actually exponential. And this, by the way, will be something that we will be repeatedly seeing in Markov decision processes, that they are super great to actually capture what we want to capture, but we need exponentially many states to represent what we want to keep in mind. But fortunately enough, there is an easier way to come up with an optimal policy just for this particular setting that we were talking about. There, we just have to have a look at these equations just directly, and we have to derive an understanding of how do we want to proceed, what is the best way of making our decisions right now. And this is not only happening here, but this is generally happening, that often you could in principle apply this algorithm, but it is much better if you first spend some time thinking about what is it that you're are expecting to see here, or what further structure do you have before actually computing everything in a somewhat brute force way. And for our example with the envelopes, this is exactly what we want to do next. So we now want to know which of these envelopes do we open first and why. Of course, we could, in principle, apply our algorithm, write this down, and now we'll even have like 8 states, depending on which envelopes we opened so far. And for each of these 8 states, we would derive what is the optimal action. But as we were seeing, most of the states we will actually never reach, and we don't actually care about what we should do there. For example, we don't care what would happen if we were allowed to open only 1 envelope or only 2. We are definitely allowed to open all 3 as long as none of them is empty. And what does this mean? How can we now simplify the question of finding an optimal policy? Well, an optimal policy in this kind of an example is nothing but defining an order of the envelopes. So do we start with this envelope, then this, or maybe first this white big one, then the small white one, then the brown one, or something like this. So all we want to do is we want to talk about different orders in which we can open the envelopes, and then we will derive what property this order has to fulfill so that it corresponds to an optimal policy. Good. So we see that any policy actually corresponds to an order in which it opens the envelopes. Now what we'll do is we'll consider an optimal policy pi star. And we now let I and j be the first 2 envelopes being opened next. When all of S has been opened before. So we are in a state S, and now the policy pi star first opens I and then opens j. Now what is it that we have? How can we write down the expected reward of the policy in the state S? Well, this is exactly given by this definition, and we can now say, okay, we first open envelope I. This gives us an expected reward of qi times vi. Then with probability qi, we continue. Then envelope I has already been opened. And there will be one fewer step. And now envelope j is being opened, so we'll get an expected reward of qj times vj. And with probability qj, this envelope is not empty. and then we will be in a state of S union I, j, and another step has passed. Good. Now what's an alternative policy? We can do the same as pi star, but open j before I. And this policy I want to now call pi. What's the expected reward of that policy in the same state? Well, we'll now just have the same thing that we have here, except for that we swap I and j. So we'll first have the expected reward from the jth envelope. Then, if the jth envelope isn't empty, we will get the expected reward from the ith envelope. Then, if the ith envelope isn't empty, then we will continue just the same way that pi star was continuing, because then both I and j have been opened. And what does this tell us? We now have that the optimal policy, pi star, is of course at least as good as this policy pi that we've just constructed. And let's first write the left-hand side. This is qi times vi plus qi times qj times vj plus qj times v star of S union qi times qj, sorry for that, times v star of S union I, j, t prime minus 2. This is the left-hand side, and that will be at least qj times vj plus qi times qj times vi. This is now what's coming from this here, plus qi times qj times v star of S union I, j, t prime minus 2. And what does this tell us? Well, this we can get rid of because it's the same on both sides. So we'll have that qi times vi plus qi times qj times vj will have to be at least qj times vj plus qi times qj times vi. And let's now rearrange this. We'll have to have that qi minus times vi minus qi times qj times vi is at least qj times vj minus qi times qj times vj. Or, equivalently, we can say that qi times vi times 1 minus qj will have to be at least qj times vj is times 1 minus qi, which means that qi times vi divided by 1 minus qi is at least qj times vj divided by 1 minus qj. And this is amazing, because we now see, okay, when do we open envelope I directly before envelope j? If qi times vi divided by 1 minus qi is bigger than qj times vj divided by 1 minus vj. And why is this so amazing? Because this here only depends on I, this only depends on j. So we immediately see what an optimal policy will have to do. Just start with the first two envelopes. Which of the envelopes will you be taking? You will be taking the envelope, which will have to be your first envelope. It will definitely have to be the envelope for which this quantity here is maximized. And then the second envelope will be among all remaining ones for which this quantity is maximized, and so on. Because otherwise there would be a point in your sequence where this inequality is not fulfilled. So our optimal policy is we open the envelopes by decreasing or non-increasing for this matter qi times vi divided by 1 minus qi. So for our envelopes, what does this mean? Which of the envelopes do we open first? Well, we can now compare, for example, these two, and the numerator qi times vi, which is just the expected content, this will be the same in both cases, but the denominator 1 minus qi, this is a half for this white envelope where it is 99 over 100 for this brown envelope. And so the larger, of course, the denominator, the smaller the entire term, which means we open the white envelope before the brown envelope. Good. So in this case, computing an optimal policy is really, really easy because it has such a simple structure, and this is something that we will see again and again, and our goal will be for some other problems also derive such a simple structure. Good, this concludes our lecture for today. We've now seen how Markov decision processes work, how we can solve them in general, but that sometimes finding an optimal policy is also much easier using the particular structure of the problem. If you have any problems, please or questions, please do get back to me. Otherwise, I hope we see each other in the next lecture. Until then, stay safe and have a good time. Bye.